What you do need to implement, because it's sort of the guts of the whole course, is integrating. So, as you hopefully have picked up from Colin's half of the course now, the way we solve problems in the finite element method is we formulate the weak problem and we integrate the weak problem over the whole domain. So what we've got to do is integrate. So suppose we have some function in some finite element space V defined over a domain omega, and what we want to do is evaluate the integral of that guy over dx. So that is the simplest integral that you could think of that actually involves a function in a finite element space. So how do we do this? Well, we only know how to do things on cells. So we turn it into a problem on cells. And the first problem we do is we say, well, integration is linear. So that means if I have integration over the whole domain, that's just equal to the sum of the integration over all of the triangles that make up the domain. So it's a sum over all the cells. So that's great. Now I'm down to cell integrals, except that I'm now doing a cell integral in global coordinates, and I don't know how to do that. Fortunately, I dimly remember passing vector calculus at some point during my undergraduate degree, and so I know that I can change coordinates on that integral. And so this is equivalent to the same thing over the reference cell, so changing the bounds, changing the coordinates appropriately, and changing the measure. But when I change the measure, I get in there the Jacobian matrix of the difference between the two coordinate systems. So roughly speaking, what you're saying is that my integral is the limit of small parcels times the value of the function as the small parcels goes to 0. And when I change coordinates from one space to another, the little parcels get stretched. And in order to get the same integral, you have to put the amount of stretch into the function, and that's why you get a determinant of the Jacobian in there, because the determinant tells you what that stretch is. So now you'll see the next convention, which is these guys are coordinates, and so the Jacobian is the derivatives of all of the components of x with respect to all of the components of big X. So now I've got another source of index to loop over, and we'll use Greek letters to index geometric dimensions, alpha, beta, gamma, delta, all the way up that set. And how do I do this? Well, we go back to our one trick. And our one trick is that everything is a function in a finite element space. So if you want d little x, d big X, we simply observe that little x is equal to the nodal values of the coordinate space times the basis functions for the coordinate space. And when I take a derivative, the derivative only hits the basis functions, because numbers don't have a derivative. And so now I've got a formula for computing the Jacobian alpha beta, which is just tabulate this guy at whichever these points are going to be. That's why we need tabulate with grad equals true, and multiply it by these guys. So notice those are different indices. This thing produces something which is matrix valued at each point, and then you can take its determinant.